Thanks for joining us today for this joint seminar from Computer Science and Engineering and Electrical Engineering. I'm Ed Lazowska from CSE, and this is also the debut of Dan Kirshen as the Close Professor of Electrical Engineering. He is close to being the Close Professor. Dan has a dual bachelor's degrees in electrical and mechanical, then got a master's and a PhD in electrical engineering from the University of Wisconsin. He's been a professor of electrical energy systems at the University of Manchester for a number of years, and will join us as the Close Professor, hopefully in March, Immigration and Naturalization Service willing. And this is an endowed position at the University of Washington in energy systems. So this creates the opportunity for many people in CSE and EE and mechanical engineering and related fields who are in and around the electrical energy systems and smart grid systems fields to work in an environment that Dan and others will create to really catapult us to the forefront of that field. So it's a great opportunity, and we're delighted to have you join us today.
Thank you very much, Ed. Good afternoon, everybody. It's a great pleasure to be here. It's a wonderful way for me to start my career at UW, as I'm learning to say. If you want about a funny accent, the one thing that Ed hasn't said is I'm originally from Belgium. Most people don't know how to recognize such an accent. So I've entitled my talk Smart Grids and Beyond. And I'm sure you have heard the expression smart grids, but there's one problem with that expression, is that if you try to figure out what it is, you probably find as many answers to that as there are interested parties. So let's, for today's purpose, use a very general definition. You may disagree with it, but let's just say a smart grid is a way of using more information technologies to improve our electricity supply. And I think what I mean by improve will become clearer in the next few minutes. And one thing to observe there is that really in terms of smart grids, you have two communities. On one hand, you have community of people who can provide lots of new technologies. You hear, Google is interested in this stuff, IBM is interested in that stuff, Cisco and so on. And then you have the potential use of these technologies, the traditional electric utilities. And those two communities don't really speak the same language. So that means there's a great opportunity for us as academics as trying to create a bridge between those two communities, and lots of opportunities for doing some interesting research. So what I'm going to try to do this afternoon is give you a flavor of some of the many questions that we could be looking at in the field of smart grids, and pulling a lot of expertise from different parts of the campus. But I think the first thing to do is really to look at what might be the drivers behind this idea of smart grids. Why is it likely to happen? And if we look at history, what drives the supply of electricity, development of supply of electricity, first thing is a reliable supply. Most of us don't like to be left in the dark, particularly when the Super Bowl is going to be on television. So that's one thing to keep in mind. The other thing to keep in mind is we don't like a big electricity bill. So the traditional driver for the electricity supply was to create this balance between, on one hand, what I like to call the greed, not spending money, or maximizing profits is another way of putting it. And on the other hand is the fear of being left in the dark. And that's particularly true for the system operator who has to do those two and doesn't want to be blamed if there's a blackout. Now, you can call that a balance, but also you could call it a stasis to emphasize the fact that things haven't moved very much, therefore, because we have had monopoly vertically integrated utilities that delivered reasonably good reliability and were usually reasonably low cost. And they were a monopoly, they were doing an okay job at least, so they didn't have a real need to innovate. So things were in stasis, pretty close to stasis for many years, at least compared to other fields of technology. But then, recently, we have this new driver that comes in, the need to go green. We're all worried about climate change, and therefore we want to look at decarbonizing the economy, and one of the big places where we can reduce carbon emissions is in the electricity supply. So now we find ourselves, instead of having a balance between the greed and the fear, we now have a triangle. We have the greed, the fear, and the green. And we have to try to reconcile these three things that pull us in different directions. It's very difficult to do all three at the same time. And you can really say that that's the area which I'm most interested in, is really how you can reconcile those three. Because some people do really interesting work on improving renewable generation, developing more efficient wind turbines or tidal stream generation and so on. Other people work on improving the reliability of the components of the power system, better insulating materials, better design for the various components. And some people look at developing techniques for reducing the costs, and both in terms of operational cost and in terms of investment cost. My particular interest is how can we improve the integration between those three drivers. And in a way, you could say smart grids is one approach to try to improve this integration, getting the right balance between those things, trying to improve all three at the same time. So improving reliability and the ability to have more renewable generation without paying a huge cost. So what I'd like to do first here is to take an example that takes this very general introduction I have given you and show how we translate that into some meaningful academic research. So let's take the problem of operating a transmission network considering the uncertainty introduced by wind generation. So the transmission network, the big transmission line you see in the countryside, is there to transport the power from the generating plants to the consumers. And the first thing we need to do if we want to look at that problem is how are we going to model this transmission network? Well, I'm not going to give you, an introductory power systems lecture. Let's just say that this problem has a certain number of state variables. In this case, those state variables are the voltage, magnitude, and angle at each node of this transmission network. And we have a set of independent variables, which are the active and reactive power injected at each node, Pk and Qk, and other control mechanisms that we have, for example, adjusting the magnitude of the voltage at each generating unit or adjusting the ratio of the transformer taps. So state variables, independent or control variables. And I just give you the equations that describe how the network operates. These equations essentially tell us that the power injected at each node in our network, each node K in our network, the active power here, the reactive power here, must be equal to the power that flows in or out of that node through the transmission lines. So this is the set of equations that describe the state of the system. To give you an idea of the size of the set of equations, if I take the continental European transmission network, which extends from Poland to Portugal, a typical model of that would have about 13,000 nodes. So we have about 26,000 of these nonlinear equations. So good sized problem, but we have known how to solve those for quite a while. And once we solve these equations, we can check whether we're operating the system in a way that's acceptable, meaning that all the flows in the lines and all the voltages at all the nodes in the network are within limits, meaning that we can continue operating satisfactorily for both the current conditions or a postulated set of conditions. So we can play what if games, what if I change the injections here or there. And we can also look at what happens if I change the configuration of the network, if I switch off a line for whatever reason or add a generator here or there. So it's a very useful tool that we can play with and that has been around for a while. Now, obviously, we try to do the best job possible. So we have a way of describing the state of the system. Next step is to try to find a way of optimizing the state of the system because we want to save money. As a parenthesis, the amount of money involved is huge. You know, the value of the electricity being sold at every day, every hour is enormous. So a small saving translates into a big pile of cash. So putting this in an optimization problem, or objective function would be to minimize the cost of producing power with the various generators. The conventional generators where we burn coal, gas, or other fuels which we have to pay for. That's what we try to minimize, but we have some constraints on this optimization problem. We have some equality constraints, which are these power flow equations I showed you that describe how power is going to flow in the network, essentially representing what's happening. And then we have some inequality constraints, essentially saying you have to operate the system in a way that is sustainable in the short term, meaning we have to respect the limits on the power flowing through the lines. Otherwise, those lines are going to trip. We're going to have problems. We have to keep the voltages within limits so we don't get big sparks. And we obviously have to keep the control variables within their limits. So this is what's called the optimal power flow problem, minimizing the cost while respecting the operating constraints of the problem. Shorthand description of this, traditional description of an optimization problem. We have the objective function, the equality constraint, the inequality constraint, and I call x naught the vector of dependent or state variables, and u naught the vector of independent or control variables. So nothing extraordinary about this. This is just one of many optimization problems of this type, except that it's a fairly large one, but it's quite sparse because of the nature of the network that we are dealing with. It's also a nonlinear problem. So this is already fairly tough, but there are good techniques to solve that these days. And I see in the audience some people from some companies who are selling programs that do a good job at this. But we want to go beyond that because bad things happen. And that's what we call in the business contingencies. Example of contingencies could be a line being disconnected because of an insulation failure. A rat decides to eat the insulation of a cable. A lightning strikes a line and creates what we call a fault, meaning resulting in a line being disconnected, which means that the power that was flowing to this line reroutes itself through other lines in the network. Or one of the generators that we had running suddenly gets disconnected because there's a mechanical problem. Or transformer blows up. I think I heard this morning on the radio that a transformer had blown up in a local utility. Not a good thing. And because we want to keep the lights on, we can't tell the consumer, sorry, we got a problem, we'll give you power back when we have had a chance to repair the transformer. No, the system has to ride through these problems, has to keep on operating. And that's why we implement what's called the n-1 security criterion, which means that if your system has n components, and if you lose one of these n, you should be able to continue running without problem. So mathematically, this is what we called the security constraint optimal power flow problem, which you can say is trying to answer the question, how should we set the control variable to minimize the cost of running the system while ensuring that the operating constraints are satisfied not just for the current conditions of the system, but also for any of the contingency states it could go in if something bad happens. So mathematically, we can formulate this as follows. We still have the same objective function. We're trying to set a control variable so that we minimize the overall cost. But instead of having one set of equality constraint, we have one set of equality constraint for the normal conditions of the system. and then one set for each of the contingency conditions, all the n possible contingencies that can happen in the system. And similarly, we have inequality constraints for the normal condition, k equals 0, or for any of the contingency states which we are considering. And then we add another constraint saying that after the contingency, we might be able to change some of the control variables to bring the system back into an acceptable operating state, but that adjustment is subject to some limits, which are summarized by this constraint here. Now, this is getting a bit more challenging, because if you look at the size of this OPF problem, it's NC plus 1 times larger than the optimal power flow, where NC is a number of contingencies I'm looking at. So if you think about, again, this pan-European transmission problem, transmission system, well, it has about 13,000 nodes, 20,000 branches, and 2,000 generators. So that's at least 22,000 contingencies that you are looking at. 22,000 times this optimization problem. It's getting interesting, to say the least, because we have to look at all of those contingencies. Now, obviously, the brute force approach is not going to work. And one of the things we're working on as part of a European project is to recognize that not all these contingencies are going to be critical. Not all the losing any of the lines is going to create a big problem. Sometimes it means nothing. So that's good, but we don't know ahead of time which ones are not critical. And also, most of these contingencies have only a local effect. If you lose a line in Poland, it's unlikely to have a big effect to the power flows in Portugal. So you might be able to reduce the impact of each of these contingencies. But again, it's not clear how much of the network you have to look at for each contingency. So that's the security constraint optimal power flow problem. But then let's bring in, and the security constraint optimal power flow is a typical example of balancing the greed and the fear. Now let's bring in the third dimension, the green, the wind generation. Wind generation, you have to build it, but once it's built, the operating cost is almost zero. Right? The wind is free. Nobody has found a way of selling it yet. So you might as well use all your wind generators whenever the wind is blowing. The problem is that you can't forecast wind with perfect accuracy. You can't forecast anything with perfect accuracy, but wind is not a particularly easy thing to forecast. So in our security constraint OPF, really we should consider introducing a vector of uncertainties describing how much uncertainty there is in the amount of power injected at each node by the wind generation. And we'll make the assumption that we can say that the uncertainty in the injection at a particular node is between a minimum value and a maximum value. So we can now go one step further and look at the formulation of the OPF problem, the optimal power flow problem, with this uncertainty. And here I take the perspective of the system operator, who is trying to make sure that security is going to be respected, meaning that the system, there's not going to be a blackout. Cost is going to be minimized, but has to accept all this wind generation being injected at different nodes over which this operator has no control, so over which there is some uncertainty. So in this case, we could formulate the problem as follows. The system operator is going to want to minimize how much change they have to make in the way the market has dispatched the generators, the conventional generators. And might also decide, okay, to ensure security, making sure that things are not going to be a problem, might have to start some additional generator, meaning there's going to be an additional cost involved in this case. But we also have now our equality constraint involve not only the state variables, the control variables, but also this vector of uncertainty. And we have also this vector of uncertainty in the inequality constraint. We still have the constraint on the changes in deviations in the cost-free variables, deviations, some limits on how much we can change the dispatch that is imposed by the market if we have a market, how much extra generation we can bring in. But because of these extra generators that we can bring in, we have introduced some decision variables, whether they are in or out. So now this problem has become a mixed integer, nonlinear optimization problem. And then we have the constraint on the uncertainties. So that's this OPF problem with some uncertainty. If you put yourself in the position of a system operator, they are very conservative people. One thing they don't want is to be blamed if things go wrong. So really what they want to know is what is the worst case? What is the worst thing that can happen? And can I put myself in a position where the worst thing that can happen doesn't create problem for me? So really they are looking at what is if I try to minimize my cost, and I find the value of the control variables that minimize my cost subject to the constraint, what is the value of the uncertainty that makes that the most difficult? And that's really, then this optimization problem becomes a max-min optimization problem. And very nice formulation, but we don't know yet how to solve this kind of problem. It's just too big and too difficult. So I think in the audience there are a few people who specialize in optimization. Well, let's have a chat at some point and discuss how we might go about solving this problem. And then you can make it even worse and doing the worst case when you're not just looking at the normal situation, but also at the security constraint optimization, where it becomes at this point totally unmanageable. So this was a slightly long and probably a bit too long discussion of the type of optimization problem that might arise from trying to balance the greed, the fear, and the green. What I'd like to do now is outline in a much more hand-waving approach a few research directions in terms of smart grids. And I'll talk briefly about three things. First is maintaining the load generation balance from the demand side. Then I could talk a bit about packet switching energy network, and then a few thoughts about what you could say would be an autonomic power system. Load generation balance. When you run a power system, you always have to have an instantaneous balance between the power produced and the power consumed. And in a conventional control paradigm, the generation is adjusted to follow the load. So here on the bottom right corner here, I have some typical load curves showing how the load varies over the day for both winter and summer. And because the winter curve is higher than the summer curve, you can tell that it's a northern European curve and not an American curve where the summer load is higher than the winter load, while in Europe it's the opposite because we don't need air conditioning. So, conventional control paradigm, you adjust the generation to follow the load. That means that you always need to keep some generation in reserve to deal with forecasting errors and contingencies. Another generator falling by the wayside whose output has to be replaced right away. Now, if we add a little bit of renewable generation, a little bit of wind generation, no problem. But if we start adding a lot of renewable generation, wind, PV, it depends on how much wind there is and on the cloud cover and whether you have a big cloud coming over your PV panels. So we don't know exactly what it's going to be. We also usually can't control it upwards. We might be able to cut it back, but usually whenever we have the wind, we use all of it. Whenever we have the sun, we use all of it. So we can't increase it in case we have a deficit of generation. And renewable generation, we do a pretty good job at predicting the load, typically less than 1 or 2%. But predicting the renewable generation is a lot harder to do, particularly if you try to do it further out in time. So in the conventional control paradigm, to keep things stable, you would have to keep a lot of conventional thermal generating plant on standby. Okay, in Pacific Northwest, you have a lot of hydro generation, but let's consider other parts of the world where they don't have that luxury. So having all these conventional thermal power plants is very expensive, and it's also going to significantly reduce the environmental benefits that you get from the wind generation, because you have to run these thermal plants part loaded where they are not very efficient. So the new paradigm would be to say, okay, instead of having generation following the load, let's try to have load following the generation. In other words, let's turn on the refrigerator when the wind is blowing, and when the wind is not blowing, let's not use as much electricity. Now, basic idea is very simple, and you may have heard all this talk about smart meters and so on, but my view is it's going to take a lot more than a few smart meters to make that happen. So here are some of the issues to look at. Many people in this audience are engineers, computer scientists, so we like gizmos, and I think we would have fun for maybe a couple days playing that and doing that manually. But after a couple days, we'd probably get bored and go back to other pursuits. So really, if you want to make that work on a large scale for the general population, it's going to have to be transparent. And it's going to have to be done in a way that consumers find easy to accept. So there's a lot of work that needs to be done in communication between appliances and smart meters, and between sending signals about when to consume and when to cut back on consuming. That's one issue. Enormous amount of work to be done there. Another issue that needs to be dealt with is, how do we optimize this response from the consumers? And we have to look at it from the consumer's perspective. There has to be something in it for the consumer. And also from the system operator's perspective. Consumer wants not to be too inconvenienced, wants to save money. System operator needs to keep the system in balance. So we have to reconcile those two perspectives. And also we have to keep in mind that when we talk about demand, if the price goes up for a part of the day, the demand is not just going to disappear. What's going to happen is going to shift to another time period. So it's not as simple as simply saying demand reduces when the price goes up. The demand actually shifts to other parts of the day, and that's much more difficult to handle. Another way of looking at that, something we're looking at that quite closely at this point, is this concept of flexibility. There's a lot of energy that gets traded, but some people are saying, well, on top of trading energy, we should be able to trade flexibility, meaning the ability to adjust the demand. If you have the ability to adjust your demand, that might have some value on top of just the value of the energy that you consume. Next, interesting area is packet switching energy networks. Now, one of the biggest advance in comms over the last 30 years is this idea that you don't need a circuit piece of copper linking the two to create a communication. in energy network, we still have that piece of copper, although very often it's aluminum, that links the generation and the consumption. And with packet switching comms, those work because you could create some buffers. Now, we could say, well, let's try to do the same thing by using energy storage to essentially buffer the energy between the generation and the consumption. Again, nice idea, but there's a problem in the sense that energy storage is and is likely to remain very, very expensive. Whenever you talk to people from, chemistry and other things, they say, yeah, we can do a lot of work in storage, but after a few beers, they'll admit that you shouldn't expect enormous breakthroughs in terms of capacity and cost. So simply putting storage to arbitrage energy use between different time periods is not really likely to happen terribly soon. But one thing that might happen is that if we want to increase the amount of renewable generation that we have, well, that generation very often is not in the right place, in the sense that it's usually not right next to where the energy is going to be consumed. So we might need more transmission lines, and let's face it, those transmission lines are ugly. And there's very, vocal opposition to new transmission lines. So we could find ourselves in a situation where we just can't build any more transmission lines. So at that point, what we would need to do is increase the utilization of the existing transmission line, because the utilization factor of current transmission lines is actually very, very low. So that might drive this idea of packet switching energy network. And that would lead to lots of interesting problem, because you want to optimize, because it's very expensive. You might want to optimize the optimization of this storage. But that has to be done under certainty, because we don't know when the wind is going to blow and so on. So you have an optimization, operational optimization over the time, over the day, over the week. And then you also have a planning optimization problem. How big should that storage be? And where should it be located in the network so you maximize the utilization of the network while minimizing the investment cost, the cost of investing in storage. But one thing we need to keep in mind is, okay, if you talk to the storage community, storage is the answer. But we have to keep in mind, storage is just one way of adding flexibility to the power system. There's going to be competition to storage from other sources of flexibility. First of them is conventional generation that can ramp up and down. And the other one is demand-side control, changing when we consume energy, as I mentioned earlier. The big one on the horizon there is electric vehicles. Deciding when we charge the electric vehicle is a way of controlling the demand side. It also involves storage, but it's a much cheaper form of storage because it's justified through some other use. For me, the cheapest form of storage is dirty clothes. Right? You decide when you do your laundry, well, you're actually choosing when you are using energy. Cheap form of storage. So packet switching energy network is going to be interesting optimization over space and over two different timescales, the operational timescale and the planning timescale. Now, last direction towards autonomic power system. If we look at the conventional way of operating power system, it's a very hierarchical way of looking at things. We have large interconnections. I've mentioned the pan-European network. In this country, we have the Western system and the Eastern system, so very large interconnections. Now, today, each control area, which is a basic unit for controlling the system, deals with probably at most a few hundred control variables. And the distribution network, which is the biggest, most extensive one, is almost entirely passive. You just feed power in, and the consumers get it at the other end. and you only have a loose coupling between the control areas. And because we don't have that much renewable generation yet, forecasting is reasonably accurate. Now, if we look at 2030, 2050 horizon, where we have a lot of demand side, instead of having a few hundred control devices, we could have a few million. And to make that possible, we would need active management of the distribution network. So instead of controlling just a big transmission network, we may also have to manage the distribution network. Instead of having loosely coupled control areas, we may have a much tighter coupling, because that's going to result from trying to exploit the economies of scope and scale to maximize the use of renewable energy resources. And the overall level of uncertainty is going to go up because of renewables, because of the possible demand-side participation, where we don't know exactly what the consumers are going to do. So the idea is, this conventional hierarchical control is probably not going to be able to handle that, the way that problem is going to grow. So really we are looking at, to use a lot of buzzwords, self-configuring, self-healing, self-optimizing, self-protecting power system. That goes a lot beyond traditional distribution automation. And the point I want to make there is that it's not simply tacking on the power system a bigger, more complex ICT infrastructure. I think it's going to take a much more in-depth look at the power system. And that's what we might call an autonomic power system, where the various parts kind of manage themselves. And to handle that, we would need to look at architecture issues, system architecture issues. How do we operate and control a system like that? We're going to need at economics, because all of this should be driven by maximizing the utility, both in terms of operation economics, where different consumers might want to trade over quite large systems, and investment economics. Traditional way of doing investment in power systems as being very much top-down, probably need to get away from that. That may not continue working. Nobody is deciding all the investment on the internet. Well, we probably need something similar in power systems. How that's going to work, I don't know. And finally, we need to keep the lights on. So the system must be resilient. We have to be able to manage the risk. And that means that instead of having those deterministic security criteria, simply saying, it has to be n-1 secure, we should be able to quantify the risk in terms of probabilities and handle it in that fashion. One thing to have to watch out for is that we don't want to get into a system where we have those low probability, large consequence events that might result from this new architecture. So these are some of the ideas I'd like to leave you with, some of the possible research direction. I know it's a very broad brush description of these things, but I hope you found it interesting. Thank you very much.
We've got time for questions. Go ahead, please.
So you mentioned that the system operators are pretty good at prediction on grid load these days. But as more and more businesses and homes embrace cogeneration with wind and solar, doesn't that blow the predictability of grid demand out of the water and thus make your OPF equations even more intractable?
Could you repeat the question?
Yes, I'm told I have to repeat the question. Yeah, so the question is, does a more responsive demand and more cogeneration by the consumer increase the uncertainty and make the problem more intractable? Yes, definitely. The upcoming uncertainty is not just the large-scale wind generation, but also what the consumers might do. And if you send them a signal saying, please consume less, you would like to know how they are going to react. Hopefully, over time, we'll learn how to do that. But in the meantime, that could be a bit challenging for the operators.
Yes, my question is, with the large scale of the security-constrained optimal power flow, two questions. First, can it be solved in real time? And if not, what would need to be developed in order to solve that problem in real time for real-time optimal operation?
Okay, the question was, can this large-scale security optimal power flow be solved in real time? And if it can't, what needs to be done to make it solvable? Well, while I was at the University of Manchester, I was part of one of those big European Union research projects where we're looking just at that question. And the objective there was to be able to solve a security-constrained optimal power flow for this entire continental European system in less than 5 minutes. So, and I think they good hope of getting there. So that's 5 minutes is considered sufficiently close to real time. Okay, you could define real time more tightly than that, but from an operator's perspective, and in a system with mostly thermal generation, that's acceptable. Yep.
Yeah, you were mentioning energy storage. I've heard of some flow batteries, like zinc bromide flow batteries, that have a projected cost of about $250 per kilowatt hour. Would that be anywhere near close to helping to balance the system?
The question is about reflow batteries and some new types of reflow batteries. Are the predicted costs going to be low enough? I'm not very good at numbers like that, I have to confess. There are some good development, and some of those things look promising. One of the issues with those reflow batteries is they're pretty nasty stuff. So lots of people are not terribly happy about seeing them proliferate. But well, we can hope that technology of storage is going to improve, because that would certainly help with the smart grids. If it doesn't, it's going to be tough.
Yeah, could you comment on what effects could have the implementation of demand response, like having the user having the ability to have energy shifting from one period of high demand to a period of lower demand on emissions? Because it seems to me that having a more flat profile on the power system demand might lead to having more baseload units running, which are generally dirtier than the peak load units. So, do you have any comments on that?
So the question is, what would be the effect of a demand response on what type of generating units are running? And a flatter load profile might result more on base load units running more than peak load units. I disagree a bit with your premise that base load units are dirtier than peaking units. Base load units tend to be more efficient and therefore pollute less than peaking units. Peaking units tend to be definitely less efficient. That's why they only use for peaks. The ideal load profile would be a perfectly flat load profile. Or if you don't have renewable generation. If you had the renewable generation, you would like it to follow the renewable generation. Because then you can run your generating unit at the maximum efficiency point, just have just the right number of generating units. Whenever you run units off their maximum efficiency point, you pollute more, you spend more money. So in that respect, the green and the greed are pretty lined up.
I think you mentioned you'd have a million or so elements to control in the year 2030, something like that?
Possibly, yes.
And I wonder if that's because you're looking at it from the top down. If you look in the United States, many homes now have solar panels, and we have electrical cars. So if you think about those as sort of the very bottom entities, we have millions of those already. And I would think a control system that not only works from the top down, but from the bottom up, where if I generate energy in my home, the most efficient thing to do would be to put it in the neighbor's garage to charge up his car. And so you'd have this microcontrol that fits in this whole system of bottom-up and top-down control of the millions and millions of elements. So are people thinking of this control problem from both sides in that way?
So the question was, we may already have millions of, or if not, already a substantial number of control devices, and if you look at it from a traditional top-down perspective, we should also look in it from a bottom-up. Well, what you're suggesting there is very much related to this idea of an autonomic power system, where small entities, in essence, can organize themselves in a locally optimum fashion, and the combination of locally optimum organize itself in a globally optimum fashion. So this is the kind of things that we need to look at, because I may have solar panels on my roof, and my neighbor may have an electric car, but we are still both connected to some electricity distribution grid, and so we are still part of the bigger system, and so that still has to work together. Mohammed?
If I can make a comment on this, it's also, this is actually what David was saying. This is the viewpoint of European for the smarter grid is just try to get smaller pool that can be self-sufficient as much as they can, and they only rely on the utility to take care of the imbalances. And then you can have the load managements and monitoring and exchange all this local. That's a big idea of the smarter grid, is to have a number of these entities.
Yes, I think you're probably going to have this development of small entities and local development. But there's a bit of an unwritten engineering rule that the Greens like the expression "small is beautiful," but engineers tend to say, well, if you make it bigger, it's always cheaper and more efficient. And if you look at wind farms these days, we're not talking about things you can put on your roof. You're talking 4.5 megawatt units that are over 100 meters tall. And you put 100 of those, you're talking centralized generation, not local generation. And so I think we're going to have both. And this autonomic power system is going to have to be able to handle both types, the very localized stuff and the very big stuff. Raphael?
You mentioned this European research project that was trying to solve, to optimize the complete European network in one shot. And in the face of it, it seems going orthogonally to the idea of pockets of locally optimized, locally autonomous systems. Is it orthogonal? What was the motivation for that pan-European study?
Right, so the question was, okay, is this European Union project about optimizing a very big system going in an orthogonal direction of this local generation and small-scale renewables? Well, you could say that European project is looking, a few years down the road, okay, not 20, 30 years down the road. Because they have a big operational problem in Europe. You start having big swings in power flows across countries that they don't really know what's happening. They have been interconnected for many years, but that was kind of a loose interconnection. Now, suddenly, because of renewables, because of electricity markets, they have those big energy transfer between countries, which make the various parts much more interacting. And therefore, the old paradigm where each country was running its own grid and just talking a little bit with its neighbors does not look very secure anymore. So they are starting to say, well, we need a way of looking at the whole thing in one go, because it's operating more and more as one system instead of a collection of loosely connected systems. So, the small is beautiful is great, but things don't always go that way.
Yes.
With the implementation of the smart grid, there are concerns about security and how it emits enough data that people with the right technology can, say, drive by a house and pick up whether they're home or not, depending on how much energy is being used. Do you have any thoughts about the security of it?
Right. So the question is about the the privacy issues, if you could call them, about the smart grid, and the fact that because of the smart grids, there might be a lot of information being available, and that might lead to privacy concerns. It's a very big issue that needs to be addressed, because one of the big drivers of the smart grid is try to harness this demand-side response, the consumer response at the domestic consumer level. And that's only going to happen if the consumers, you and I, are comfortable with that happening. And therefore, we need to be comfortable that data doesn't fall in the wrong hands. Recently I got some recordings of data from some field tests that had been done about domestic energy consumption. And we were looking at those energy profiles. It's very interesting to see, I didn't know which houses it was, I promise. I didn't go invade anybody's privacy, just numbers for me. But you can start saying, this is a completely different pattern in this house from that house. So you can kind of tell what people are doing. So I'm sure that some people with nasty minds would find a bad way of using that if it fell in the wrong hands.
Then optimize, maximize, and minimize. They don't use S anymore.
Did I forget any S in in translating this from British English to American English? Well, I've lived in the UK for 16 years, so it took me a few years to learn the British spellings, and now I'm going to have to relearn the American spellings.
Okay, let us thank Dan again. We'll see him here in March.